Hello, guys. So, welcome to our Tuesday lecture. So, in this lecture, we're gonna explore a new BGT amplifier configuration, which is the common collector amplifier. So, we discussed the common emitter amplifier, and we discussed also the common base amplifier. Each one has its own advantages and disadvantages. Okay. So, the common collector amplifier, which we're gonna discuss today, has its own characteristics as well. So let's explore its amplification and our input and our output, and then based on our analysis, we're gonna explore or we're gonna know what kind of application we can use this new configuration in. So let's have a simple example for it. So let's draw an example for it. So we have here. This is a simple example for a common collector. So we have here the input at the base. This is the input connected to the base. And here is the output. The output is connected to the emitter. So the output connected to the emitter. And since the collector has no input or output connected to it, so it's common for us. This circuit has also another name, and by the way, this is the most famous name rather than this common collector amplifier. It's called also emitter follower. Emitter follower. And we gotta know the reason behind this naming, after we make our analysis and this find out the voltage gain of this guy, this new circuit. Okay. Good. So let's deduce or get the equivalent circuit, EC equivalent circuit of that circuit here. So here is the AC equivalent circuit of the transistor itself, beta IB. Oh, here is RE or RB, R by. Here is IB. Here is the emitter, here is the base, here is the collector. And we continue the other part of the circuit. So in EC, the DC sources are cancelled. So VCC will be connected to ground. So there's another color here. This guy will be connected to ground. So the collector is basically connected to ground. Good. Another DC source that we should cancel is the current source. So this current source should also be cancelled. So it will be open circuit here. And if it's open circuit, then you can just ignore it. And the capacitor will be short. So the emitter here will be connected through RL to the ground. Like this. Then we have lastly the base. The base is connected to our signal, then V signal, then the ground. Good. And before we continue, here is IB, here is beta IB or IC, here is IE, and here is VO. VO is the voltage across RL from the emitter to the ground. And the input is between the terminals of R input, and R input is between this point, the terminals of the source or the signal, input signal. So this point here and the ground. So this should be the input here between these 2 points. The base, this point, which is the base, and the ground. Good. So let's find out our, basic characteristics of any amplifier. Our input, our output, and EV, the voltage gain. So number 1, our input. Sometimes I call it RI or RIN. All are the same. Good. So what is our input? So if we imagine, so basically our input is between these 2 terminals, this terminal and the ground. So it's equal to V input over I input, assuming that there is a current here called I input flowing in that branch here. So it's equal to V input over I input. Good. So what is V input? V input is the voltage between this point and the ground. So if we make a loop here, a loop like this, we find that V input is equal to IB R by, the voltage across R by, plus the voltage across RL. And the current in RL is IE, which is beta plus 1 IB. So plus beta plus 1 IB RL. So this is equal to, let's take IB as a common factor. So we end up with R by plus beta plus 1 RL. And I input is basically IB because they are in the same branch. So our input, if we divide these 2 together, will be IB R by plus beta plus 1 RL over IB. IB will go with IB, so Rn will be equal to R by plus beta plus 1 RL. We know that R by is hundreds of ohms to few kilo ohms. Let's say it's 1 kilo, okay? And RL usually, and beta usually in hundreds, 100, 150, 200. This are typical values, okay? And RL usually also, we can say, let's say 1 kilo ohm. So if you multiply 1 kilo ohm, which is RL, by 100, then this will give you 100 kilo ohms, okay? So based on that analysis, we now see that the common collector amplifier or the emitter forward circuit has usually very high input resistance. So this is the first advantage of the common collector amplifier, very high input resistance. And why is that? Because of the inclusion of beta here. So beta, because it's 100 usually, when it multiplied by something, it will be magnified 100 times. So this is, of course, will increase our input resistance. So this is the first advantage actually of the common collector amplifier. So good. So let's go now and calculate our output. So I want to go back. Yeah. RO number 2. RO. So RO is resistance seen by the load. So we must remove the load testing voltage source like Vx that produces Ix, and RO will be Vx over I. So let's do that. So let's draw the same circuit again, and we can just make a copy and paste of it to not waste our time. Here it is. So I'm gonna remove our load. And put a testing voltage source instead of it. So I'm gonna put here Vx, which reduces Ix. And of course, don't forget to cancel the independent sources, which here is the V signal. So we should also cancel V signal by shorting it. So I'm going to replace this guy by short circuit. Okay, good. So RO is equal to, let's go back to the blue color, equal to Vx over Ix. Good. So what is Vx and what is Ix? So at that node here, Ix is going into the node, beta IB is going into the node, and IB is also going into the node. So Ix plus beta IB plus IB equal to 0. So from this, Ix is equal to minus beta plus 1 IB. Good. How about Vx? So if we take this loop here, let's enlarge it a little bit. This loop, so Vx is in that direction. IB is flowing in that direction, so positive, negative. Flowing in that direction, so positive, negative. So this voltage is that direction. This voltage is also in that direction. So all of them are the same direction. So Vx plus the voltage across R by, which is IB R by, plus the voltage across R signal, which is again IB R signal, equal to 0. So Vx is equal to minus IB R by plus R signal. Good. So both now Vx and Ix are a function of IB. So we can divide safely now because we know that IB will just go away. So Vx is minus IB R by plus R signal over minus IB multiplied by beta plus 1. So this will go with this, minus also goes away. So we end up that RO equal to R by over beta plus 1 plus R signal over beta plus 1. Okay, good. So, or we can just, leave it like this. Both are the same. Some people also like to substitute R by over beta plus 1 with RE. You remember, guys, RE, this resistance in the other AC model for transistor is equal to R by over beta plus 1. So some people also like to write it in that way. Because RE usually, if you see, guys, here, R by, we know that it's a few hundred to kilo ohms, to few kilo ohms. So if we divide it by beta, which is, 100 or something, or even more than 100, then we end up with something in ohms. Okay. So usually, and also our signal, maybe it's 1 kilo, 2 kilo, something like this, even 10 kilos. then you will divide it by beta, then you attenuate or lower its value 100 times. So for that reason, RO, the output resistance of the common collector, usually very small. So let's write this in red. This is very small resistance. So till now, we find out that the common collector has a high input resistance and a low output resistance. And these are two, basic advantages of the common collector. Okay, let's continue and see. How about AV? Let's have another page. I don't think now we can continue here. Number 3, AV. AV is VO over VN. I will deduce AV now, and based on AV, we can get the open loop voltage gain. Okay, you remember, guys, there is voltage gain and open loop voltage gain, and open loop voltage gain is just the voltage gain when the R load is equal to infinity. I can do AV first, then AV naught or the open loop voltage gain, opposite to the way we did before. Before we get AV naught first, then AV, but we can do the opposite as we will see now. So VO over V input. So let's let's put the circuit again for our convenience. Good. So VO is the voltage across our load. So it's equal to the current in our load multiplied by our load. The current in our load is beta plus 1 IB. And our load is our load. Good. How about V input? V input again is the voltage between the source C at the terminals of the source. So the source is one part, which is V signal and R signal together. So it's a voltage from this point to the ground. So if we make a loop here, V input is equal to the voltage across R by plus the voltage across RL. So I will write it in that way now. It's IB R by plus VO actually. The voltage across RL is VO. So before I continue, I will just write this here before we continue. It's VO, and the V input is IB R by plus VO. And before we continue now, we know that EV is less than 1. So we got enhancement in our input because our input increased. We got enhancement in RO because RO decreased. But till this moment, EV attenuated or EV reduced. It's less than 1. It's not amplification. So this is less than 1 because, of course, when you divide something by the same stuff plus other thing, which is positive, then you'll get something less than 1. Okay? So let's continue and see how far we reduced the voltage gain. Maybe this IB R by is small, maybe. Let's see. So IB R by, and the VO is beta IB, beta plus 1 IB RL. This is VO. Okay. So let's divide those. EV is equal to VO, which is beta plus 1 IB RL over the input IB R by plus IB beta plus 1 RL. IB, all those guys will go together. So we end up with beta plus 1 RL over R by plus beta plus 1 RL. And here is the trick. Yes, it's less than 1, but usually, beta RL is much larger than R pi. That's why so usually, let's write it, beta plus 1 RL much larger than R pi. Why is that? Because even RL is small, it will be multiplied by beta, which is, usually 100 or something, or even more. So it will be magnified 100 times. Okay. So based on that, this will be approximately most of the time. Of course, in any problem you solve, you should analyze it and get the accurate number. So usually close to 1. So it's not that attenuation. Okay, usually it's close to 1. And it will become clear now if we calculated the open loop voltage gain. So for number 4, the open loop voltage gain, which is AV naught, which is AV when R load equal to infinity or open circuit, right? So let's do that here. So let's divide the numerator and the denominator by RL. So we'll get up with beta plus 1 over R pi over RL plus beta plus 1. So if RL goes to infinity, we will end up with beta plus 1 over beta plus 1, which is 1. So it's clear here from AV note that, yeah, the voltage gain is close to 1. Even if RL is small. But because it will be multiplied by something in hundreds, like beta, then beta plus 1 RL will be much larger than R pi. Okay? How about the last stuff? Number 5, the overall voltage gain, GV. GV is equal to AV, R input plus R signal. So AV is close to 1. And our input is, let's write it down. It's, where it is, it's R pi plus, yeah, beta plus 1 RL. Over R pi plus beta plus 1 RL plus R signal. Again, if we designed the circuit such that beta plus 1 RL is large, and by the way, you can do that because you can choose a transistor, so you can choose a transistor with very high beta. Then, if our input is much larger than our signal, you will end up that GV is equal to 1. So it's not that bad. So you get enhancement in our input, you get enhancement on our output at approximately the same voltage. Input, the same voltage will be in the output. So you will not lose. Okay.